Hi everyone, welcome to the AA Crack channel. I am Akash Gangwar and today we are kicking off the PGDBA 2026 lecture series. Last year we received feedback that some of the videos weren't detailed enough. So this year the series will be more thorough and comprehensive than before. Also, unlike previous editions, the questions discussed in these lectures will now be included in the Prep Master series notes. So let's get started with our first lecture on logarithms.
So let us start with the definition of log. So forget about this particular written definition. Let's see what log exactly means. Before starting what log means, we must be knowing that a raised per x equals to n. We must be knowing this kind of equation, right? So if we want to write this in terms of log, we'll be writing log base a n equals to x. So actually, both of these equations are interconvertible. So basically, that means this can be converted to this, and this can also be converted to this. Both means the same. So log base a n equals to x. So x is actually the power over here. A is actually the base over here, and n is actually the outcome or input, you can say, right? Outcome over here, input over here. So this is how we can understand what log actually means. So let's discuss the certain restrictions or conditions on base and input. So let's say we have log base a n equals to x, right? So the first condition we have is a should be greater than 0. Second condition is n is also greater than 0. Third condition is a should not be equals to 1, right? So these are three conditions. Let's understand all these conditions one by one. So first of all, the other condition is a is less than 0. Why this is not true? Let's see. Let's say we have log of minus 10 in 10, and again we have log of minus 10 in 100. Now in this case the answer would be 2, but in this case we cannot define any answer, right? Because that would actually mean 10 raised per x equals to 10 minus 10 raised per x equals to 10. This doesn't mean anything, right? We know that. So in certain cases negative base is working, because over here minus 10 raised by 2 equals to 100, that is working. But over here we're not getting any kind of value, because minus 10 raised per anything won't be equal to 10, right? At least in terms of real terms, right? So in certain case this negative base definition is not working, in certain cases it's working. So we cannot definitely define one particular definition of log for negative bases. So that's why a less than 0 is not working. Now let's look at the second case. Second case is we are also restricting a should not be 0, right? So let's take a equals to 0, and we have n and we have x over here. So that basically means 0 raised per x equals to n. That obviously means 0 raised per x equals to 0 only, because 0 raised per anything should be 0. Now x can take any value. Again, we're not getting one single value over here, because we have base as 0 over here, and that is against the definition, right? We should be getting one consistent value over here. So we're not getting that. So that's why this is also rejected. Now, what is the problem between for a now for a equals to 1? So let's look at that. Let's say we have log of 1, and this is, let's say, n, this is equals to x. So that basically means 1 raised per x equals to n. That would definitely mean that n should be 1, right? 1 raised per x equals to 1 only. N should be 1 if that is the case. So again, x can take any value. Or you can say in other terms, let's say this value is 5 or 4, let's say, right? So 1 raised per x equals to 4, that is not possible. So if we have base as 1, we cannot define log for any other number, right? We can just define log for just 1 and nothing else. So that's why this definition is also inconsistent. So that's why a is not equals to 1. Now, what about n less than 0? So log a, let's say we have minus 10 equals to x. And now since we have made the conditions, so a is always positive, right? So a raised per x equals to minus 10. That is not true, right? If a is positive, we have proved that a should be positive. In that case, a raised per anything that won't be equals to negative number. So that definition is not consistent. Now, if we talk about n equals to 0, because again we have conditions n greater than 0, so it cannot be negative, it cannot be 0. Let's say this is 0. Again, if this is 0, this has to be 0 for any value of x, right? So if I'm doing a raised power x equals to 0, this can be 0 only when a equals to 0. Otherwise, it won't be 0. It can be closer to 0, it won't be 0, right? So that's why this definition is also inconsistent. So these are the restrictions which we are going to follow for log. A and n both greater than 0 and a not equals to 1. So these are the three restrictions for log a n equals to x. Log base a n equals to x. Okay. So let's look at one example. The number log 2 9 is an integer, rational number, irrational number, prime number. So definitely it's not a prime number, and definitely it's not an integer. That is quite visible, because log base 2 4 sorry 8 would be 3, and log 2 16 would be 4. So this is something between 3 and 4 which is neither a prime nor integer, right? So both these options are actually rejected. Now, how to differentiate between rational and irrational number? So we know that by definition, a rational number can be written in terms of p by q, where both p and q are actually co-primes, right? Co-primes mean they both can't be further subdivided. Co-primes. So 3 by 4 or 4 by 5, these are co-primes because they have just one common factor. They cannot be further subdivided. 4 by 20 is not 4 by 20. Both these numbers are not co-prime because they can be further subdivided. But 4 by 5 cannot be, 3 by 4 cannot be. So this is the definition of a rational number. So let's assume that this is in terms of rational number, right? So log 2, sorry, log base 2 9 equals to some rational number p by q, right? So if we go by the exponential definition, that would mean 9 would be equals to 2 raised power p by q. So if we if you raise both the equations, both the sides with the power q, we'll be getting 9 raised power q equals to 2 raised power p, right? And we know that this cannot be true. This is an odd number, this is an even number. Both q and p are integers, right? So odd number raised to some integer and even number raised to some integer, this is always going to be even, this is always going to be odd, and they both cannot be equal. So our assumption, basic assumption, that p by q, this is a rational number, this particular entity is a rational number, is false. So basically that should be an irrational number, right? Now let's talk about properties of log. Log a base a 1 equals to 0. That is quite obvious, right? So let's see. Let's write in the exponential form. We'll be getting 1 equals to a raised power 0. Now we have the basic conditions: a not equals to 1, a greater than 0, right? So we know that any number raised power 0, that should be 1. So the proof is quite simple and quite obvious, right? Now the second property, log base a equals to 1. Again, if we write this in the exponential form, we'll be getting a equals to a raised power 1, right? And that also makes sense. Anything raised power 1 is a itself, a raised power 1 is a itself. So that should be equals to a. So this property is also quite obvious. What we'll be getting? We'll be log of a m dot n equals to x plus y. Now what was x plus y? That was log a m plus log base a n, right? So that is how we have proved the property. Now let's talk about property number 4. That is more or less similar to the property number 3, but we have just a negative sign over here. So again, let's say this is x, this is y. So we'll be writing log base a m equals to x and log base a n equals to y. That would be giving us m equals to a raised power x, n equals to a raised power y. Now if we divide both of them, because we have division over here, we'll be getting m by n equals to a raised power x minus y. If we again write this in the log form, we'll be getting log of a m by n equals to x minus y. Now x minus y can be replaced from here. That is log a m minus log a n, right? Now the last property for this lecture, that is log base a m raised power alpha equals to alpha times log a m raised power alpha. That is equals to, let's say, b. Okay. So that basically means m raised power alpha equals to a raised power b, right? Now if we raise both RHS and LHS with the power 1 by alpha, we'll be getting m equals to a raised power b by alpha, right? Now let's try to write this in the form of log. Okay, so we'll be getting log of a m equals to b by alpha, right? Now if we cross multiply alpha over here, we'll be getting alpha times log of a m equals to b, right? And b was this only. So this is how we can prove this property. So today's lecture was till here only, and this was quite a short lecture because this is just the starting. And once we get along with the content, we'll start picking up the pace. Okay. So notes, examples, and quizzes related to this particular lecture will be uploaded in the Prep Master portal, and there will be certain other problems as well. Okay. So yeah, let's meet tomorrow in the next lecture. Thanks for watching.